now that we've gone through the example of these ZTC current reference design, I want to take the time to just make a few comments about the trade-offs between the various current mirrors that you can use in a design. So to begin, I'm going to list the different types of current mirror temperature dependencies that we have. One of them is CTAT, which is complementary to absolute temperature. The second one is PTAT, which is proportional to absolute temperature. And then the third one is ZTC or ZTAT, which is no curvature with respect to temperature. Now, one of the benefits of the CTAT architecture is that it's actually nice for biasing a constant overdrive with respect to temperature. And the reason for that is if you look at the overdrive equation, that is 2ID over K prime W over L, and K prime has mobility embedded within it, and as temperature is decreasing, mobility is increasing for decreasing temperature. So we would need to proportionally change something in the numerator to maintain a constant overdrive. And that's what that does. So this architecture is good for constant overdrive VOV. And an application where you might use that would be if you're extremely headroom constrained on something, and no matter what your performance looks like, you must maintain that this is an architecture that you would need to utilize at the expense of power dissipation at the lower temperatures. And oftentimes that might be useful when you've got a very wide temperature range that you're trying to deal with. And now if we look at PTAT, on the other hand, if you look at the expression for your unity gain bandwidth, this is GM over CC, and it's directly proportional to your GM, your transconductance, right? And GM is equal to 2ID K prime W over L. So now what we have are the terms both in the numerator. So what you need is you need a current that's changing opposite now to mobility, right? Because this mobility dependence still holds. So here we would get that if we use a PTAT reference. So the benefit here is that if we use PTAT, then it will help us with our stability margins across temperature. And you might have a design where you're trying to push the limits on your performance, and oftentimes it will be very difficult to achieve the stability margins that you're looking for across PVT. But by utilizing a bias like this, it reduces the demands on that somewhat. Of course, the drawback here is what we just discussed, that overdrive will not remain constant. So you're going to have to live with a reduction in your maximum output swing or your ICMR or whatever the spec may be. So, and then the last option that we have is ZTC. ZTC is nice, if you're pushing the limits on something like power dissipation. But the mindset that you need to break out of is that you don't always need ZTC. You don't need something that's super precise across temperature. Sometimes you do want this dependence that's proportional or complementary to temperature. ZTAT still does have its uses. I find myself using it when I have a very large scale factor. So if you have a class AB output stage and relative to your reference current, it's gained up by, say, a factor of 1,000, then any slope that you have on CTAT or PTAT would drastically increase your power dissipation. So that would be a good reason to use it for ZTAT to maintain power margins. And again, you know, there's many different ways to bias your circuits. You kind of just need to step back and assess which one of these three would be best for your application. Which of your performance parameters is most critical, and also you have to ask the question, of these performance parameters, is one more difficult to meet than the others? And that might lead you to favor one bias over another for that particular design.